As we turn our attention to absolute extreme values, we are going to look at the extreme value theorem. And as in R2, there's one in R3. If f is continuous on a closed and bounded set in R2, then f attains an absolute maximum, we'll call it f of x1, y1, and an absolute minimum, f of x2, y2, in D. Closed means that it contains all of its boundary points. Think about an interval in one dimension. Think about an interval on the number line with square brackets instead of parentheses. Bounded means it's a finite region. In other words, given a surface, if we take just a piece of it, then on that piece of it, there will be a biggest output and a smallest output. That's what this says. That is called an existence theorem, but it doesn't tell us how to find them. So we're going to write down, to find absolute extrema, what we do is evaluate f of xi, yi at critical points, find extreme values on the boundary of D, and then of these, the largest z value is the absolute maximum, the smallest z value is the absolute minimum. This is very analogous to R2. You find critical numbers, you evaluate at the endpoints of the interval, and then the largest output is the max, the smallest output is the min. But now here, the wrinkle is that we find extreme values on the boundary of D, and that can be a little bit confusing, but we'll work through that in our next example. This example is, find the absolute maximum and minimum values of f on the set D. Our function f of xy is equal to x plus y minus x times y. D is the closed triangle with vertices 0, 0, 0, 2, and 4, 0. First things first, find critical points. Fx is equal to 1 minus y. Fy is equal to 1 minus x. So we can see that 1, 1 is a critical point. We'll set that aside and come back to it in a little bit. Now let's consider this region D, the closed triangle. I decided I would go ahead and use a grid. Here we have our triangle with vertices at 0, 0, 0, 2, and 4, 0. What happened there? I lost my point there. And we need to consider each of these segments that form the boundaries of the triangle separately. So the segment from 0, 0 to 4, 0, I'll call it L1, or it's part of L1, and it's the equation y equals 0, right? It's the x-axis. The segment that goes from 0, 0 to 0, 2 is, of course, along the y-axis, and I'll call that L2, and it has the equation x is equal to 0. The segment that connects 0, 2 to 4, 0 is part of the line that I'll call L3, and it has an equation y equals 2 minus 1 half x. We'll take each of these in turn. For reference, I'll go ahead and put f of xy as it was stated at the outset of this, and it's x plus y minus xy. Along the curve y equals 0, we replace y by 0, we end up with f of x0 is equal to x. And we can see that if f of x0 equals x, then the smallest value along this boundary is going to occur when x is 0. The largest value is going to occur when x is 4. So f of 0, 0 is equal to 0. F of 4, 0 is equal to 4. Now we set that aside and we're going to turn our attention to what's going on along x equals 0. And folks, what we're doing, I'm doing this in this order, but it'll make a little more sense when we get to L3. So just sit tight. Along x equals 0, we're looking at the function f of 0y, right? Replacing x by 0. And that's going to give us y. Again, we have a smallest value on this segment when y is 0 and a largest value when y is 2. F of 0, 0 is 0. F of 0, 2 is equal to 2. And eventually what we're going to do is we're going to compare all of the outputs that we're getting here. But one more step. Well, several. Along the line y equals 2 minus 1/2 x, we're now considering the function f of x, comma, 2 minus 1/2 x. You see, we're going to replace y by the expression 2 minus 1/2 x. And f with that replacement becomes x plus 2 minus 1/2 x minus the quantity of, minus x times the quantity of 2 minus 1/2 x. Now that simplifies to 1/2 x squared minus 3/2 x plus 2. Here we have a function only of x. That should make sense because we replaced y. I'm going to rename it. I'm going to call it g of x. To find out the maximum or minimum values along that curve L3, I need to find out the maximum or minimum values for g of x. So I'm going to take its derivative, g prime. And g prime is equal to x minus 3/2, which means that x equals 3/2 is a critical number for g of x. For f of x, we need a y value, and for that, we turn back to y equals 2 minus 1/2 x. If x is 3/2, then y equals 2 minus 1/2 of 3/2, which simplifies to 5/4. What we can say now is that as far as g is concerned, x equals 3/2 is important. And that translates to, as far as the hypotenuse of this triangle is concerned, the point 3254 is important. We need to evaluate f at 3, did I say 3, 2, and 5, 4? Oh my gosh. 3/2, 5/4. And using our original definition of the function f, if we evaluate that when x is 3/2 and y is 5/4, we get a value of 7/8. Let's kind of map all of these out on our graph here. At 0, 0, we have that z is equal to 0. We found that out when we were looking along x equals 0 and along y equals 0. At 0, 2, we found that z is equal to 2. At 4, 0, we found that z was equal to 4. Along L3, at the point 3/2, 5/4, we found that z was equal to 7/8. So just along that curve, we'll say, the z value dips from 2 down to 7/8 and then back up to 4. Now let's not forget that 1, 1 was a critical point. F of 1, 1 is equal to 1 plus 1 minus 1 times 1 according to our function definition. And so f of 1, 1 is equal to 1. So we have a point interior to our region where the z value is equal to 1. So here's what we need to do. For all these z values that we wrote down, we need to identify which one is the largest and which one is the smallest. Our z values in order are 0, 7/8, 1, 2, and 4. Of all of these, z equals 0 is the minimum and z equals 4 is the maximum. So we can conclude this by saying the absolute minimum is 0 and the absolute maximum is 4. Now I've kind of laid this out in such a way that it's kind of all over the place. A different organizational structure would have been to set up a table, xy, and then f of xy, which is x plus y minus xy, and jot down all of the information that we had, right? 1, 1 was a critical number. Excuse me, that's not true at all. 1, 1 was a critical point. This is a point. xy is a point, not a number. All right. And then we found on the boundary we cared about 0, 0, 0, 2, 4, 0, and finally 3/2, 5/4. And those outputs were for 1, 1, 1, for 0, 0, 0, for 0, 2 it was 2, for 4, 0 it was 4, and for 3/2, 5/4 it was 7/8. And of course, looking at this list, we can see that 0, 0 is the absolute minimum. And that wasn't true at all either. 0 is the absolute minimum. My gosh. And 4 is the absolute maximum. So now the question might be like, why did we even care about 7/8? I mean, it turned out not to matter in our answer. Well, we didn't know it wasn't going to matter. We knew that that was the smallest value. I mean, it turns out to be the smallest, but we knew that that was an important thing that happened along one of the boundary curves. We don't know what the relative size of that is until we see all of the sizes of all of the important values that we're coming up with. To help see what's going on with this, I have graphed this in GeoGebra. Here we see we have the x-axis, the y-axis, and the hypotenuse of the triangle, which is on the line y equals 2 minus 1/2 x. And I've entered these as curves on the surface. And what we can see is there's a smallest z value, and it occurs when x and y are 0, and the z value is 0. There's a largest z value for this region on the surface, and it occurs above the point 40 on the x-axis, right? It has a value of 4, so the minimum value is 0, the maximum value is 4. We can also see that along the above the hypotenuse, right, along this boundary curve, it's a parabola that itself has a minimum value. We found that when we found g prime and its critical number. It just turns out that the smallest value on that curve, on that parabola, just isn't smaller than the output at the origin. But we didn't know that until we compared all of the output values. I thought I was done with this, but I realized I needed to say one more thing. What about the point 1, 1, 1? Well, we have here that point. I plotted it interior to the region D, and it's on the surface. And what we can see is that from a certain vantage point, we have a local maximum of 1. But if we rotate it a bit, then we see that we have a local minimum of 1. And so the point 1, 1 is actually a saddle point. It didn't contribute to our final answer, but I did want you to know what was going on at that point.